So is that kind of like a buffer solution then?
Kind of. So yeah, so buffers are related to equilibrium. All right, let's get started. So any questions before we get started with our lecture? And then I was still kind of grading your quizzes, but I'll have those probably back to you, hopefully in lab. Most people did well. There are a few people that kind of bombed it. But right, just look at your rate loss summary cheat sheet. I feel like everything is like literally on this page, and that really just cuts down on the chapter. And then just other announcements. Sorry, my computer's being like a tad slow today. Uh, so don't forget we are at week 9, so end of the quarter. So I don't know how we got there. Yeah. So not the week of the exam, no. So these are our last 2 chapters. So we're basically doing equilibrium and then more equilibrium. So equilibrium is just going to kind of keep going through. Let me see if I can pull up. Sorry, I really should have restarted my computer apparently before. I don't know why it's being slow. Well, I probably didn't want to do that. Sorry, I was just trying to pull up our syllabus. So we're almost to the end. Oh, and so this is our last lab, the equilibrium lab. So I really like this one. It'll be a fun one. But then next week we'll do our kind of lab final activities, so whatever that will be, right? Our exam. So probably a small lab practicum. Correct. So no lab week 11. I need to give myself time to grade. Y'all know that I get in a crazy grading hole. So that's what I'm trying to prevent. Jeez, I don't know what is wrong with my computer. Yeah. So yeah, we'll kind of do that. And then if anybody needs to make up labs, so we should either do that this week or next week with the final And then, right, you'll have your lab final and your respective kind of lab days as well. And then don't forget about the paper. So I've seen some people's papers, so email me if you need sources. I don't know what is going on with like the internet. I was just trying to pull up the syllabus and it's like not loading. It's really being. So I'm going to try to close Firefox in the meantime. But all I was trying to get at with the equilibrium is we're going to be doing equilibrium kind of this week. It ties into, so people were kind of asking questions about like buffers, so it ties into acids and bases. We'll continue it next quarter as well. Again, I was trying to pull up the syllabus. I'll get that going in a second. But we'll see it continue with like solubility. So I've kind of teased that, like back in first quarter, we like looked at the solubility rules. Sorry, still trying to just restart my computer a little. Geez, too many. Yes, I'm trying to close all my tabs. I'm sorry. All right, trying to restart that. All right, so then kind of where we are. So again, we were looking at reaction rates and kinetics, right? And again, kind of how far the reaction goes with kinetics. We saw that tie in with the mechanism last chapter. And so then we just want to get into a few reminders. So looking at our equilibrium, right? So we're getting into equilibrium, but we don't want to confuse equilibrium and resonance. And so just a quick reminder is resonance is when you have just the movement of electrons. And so again, with resonance, right, we're not changing any bonds. Usually we're just shifting around our double bonds or our pi bonds as we want to start thinking about them as. And so we're just usually moving, right, 2 electrons as well. We've kind of touched on radicals, so we'll look at radicals again here and there as we finish out the year. And so with resonance, we use this double-headed arrow, right? And so this is different from our equilibrium arrow, which is these 2 half arrows, right? And then we may have, let's just say we're looking at some general dissociation, AB, and then, right, makes A plus B there. And so that's equilibrium. And so equilibrium, and people were kind of asking questions, and I think they were good questions to kind of start off as, but just putting us in the correct mind frame for equilibrium. And we've kind of discussed this, like the concept of equilibrium, such as like vaporization, but you have this sort of back and forth reaction, right? So even though it may reach a steady state concentration of equilibrium, which, like I said, you'll do in lab today, so that'll give you a really good review. But what's happening is there's still a reaction going on, right, in both directions. So on an individual, right, molecular level, so they're still being split apart or coming together. So there's still a lot of action, right? So there's still reactions going back and forth, but the overall concentration at least doesn't change once we're in equilibrium. And so just thinking of kind of real world examples and kind of relating to different proteins. And so looking at kind of fetal hemoglobin, this is interesting. So I'm not much of a biological chemist. I think you guys have gathered that, but I still like looking at these structures here. And so it mentions that the fetus has a higher affinity for binding hemoglobin, so the fetal hemoglobin, and it's showing the structure here. And so it mentions that there's a difference in the folding, which I thought might appeal to some of the more biologically minded people in the class. So where does it say? So they have, right, 4 subunits, but in fetal hemoglobin, the beta subunits are replaced with these 2 gamma subunits, and so that's what causes the increased affinity for oxygen binding. And then I just kind of linked this article because this was kind of interesting that they're kind of studying, mutations and kind of the protein folding, and again, seeing the implications that that might have for, in this case, right, sickle cell treatment. So just kind of interesting. But let's think about the hemoglobin and this equilibrium, right, and kind of what's happening. And we could just think about it kind of more simply, right, without getting into the maternal versus the fetal hemoglobin exchange. Well, let's just first think about how hemoglobin works, right? And so your hemoglobin is your protein, and right, mainly iron based, so it can bind that oxygen. And so your hemoglobin, let's just say it starts off in your lungs, and then there's going to be, right, a higher concentration of O2 in your lungs. So that's going to drive the binding of that oxygen right to your hemoglobin. Then it'll go out of your lungs and maybe go down to your leg, right? And you've been walking and running. And now there's a less of a concentration of oxygen, right? Because your leg muscle has consumed it. And so that equilibrium will cause the O2 to unbind. And so now it unbinds in your leg, and then, right, the hemoglobin then goes back to the lungs and repeats that cycle, obviously, over and over. And so I've mentioned this in the past about CS2, right, being toxic. And so part of that goes back, right, to the binding affinity of hemoglobin. So that iron is going to bind pretty tightly to sulfur potentially, so that's where the toxicity comes into play. So, right, again, it's more difficult to liberate the CS2. And so this again just kind of goes over it. And then if we look at, again, now the fetal hemoglobin, the key in that is the equilibrium constant is larger than the adult hemoglobin constant. So then that's why right, then the baby is able to still get oxygen as opposed, right, and that's why it doesn't take it from the mom, since it's more efficient at binding the oxygen, so it can operate, right, at lower concentrations of O2. And so then it's still transferred then, right, from the mother's hemoglobin to the fetal hemoglobin, again, with that higher binding affinity. So that's what makes it able to happen. And then we're kind of starting to see these kind of reaction dynamics, and this is what we'll be getting at and solving and, right, finding the equilibrium. But essentially we'll have a reaction start, our reactants will be consumed, products will be made, right, and then it'll stop once we reach, again, our equilibrium conditions. And then, right, we'll still have products reforming reactants and vice versa. And again, this is assuming that products are not allowed to escape. And so this is where we can think of ways to drive reactions forward. So now's a good time to perhaps mention reactions like condensation reactions, which, again, we'll bring this up again third quarter, but I like showing, and I may have talked about it before, but it's still good review and a good reminder. And so there's these condensation reactions, and so they can be driven forward by kind of this equilibrium, or we've talked about Le Chatelier's principle in the past. Oh, we don't. Let's just stick to this one. So, right, reaction here, then you start refluxing it, boiling it, and if you're doing a condensation reaction, you're producing water, and so you can see that your water would start to accumulate here. You'd want to select an organic solvent, right, that's less dense than water, so that water's at the bottom, your organic solvent is on top. If you really generate a lot of water, right, you could drain it. That's what this little stopcock here is for. You just drain the water out, continue pushing your reaction forward. And so that's the implication, right? That's kind of what they're saying here. That assuming that the products are not allowed to escape, right? Again, that you're just going to be stuck in this equilibrium. But then part of where you get into like the design side of a reaction, or even, you know, we always mention the Haber-Bosch process of making ammonia. Well, all of that is, well, how do we continue to drive that reaction forward, right? And that could be, how do we distill off some of the products so that these can keep reacting at difficult conditions, right? So going back to the condensation reaction, how do you get rid of water to keep that reaction driving forward? Or, you know, whatever products you want to escape or, again, continue pushing the reaction forward. So just something to keep in mind. And so again, we're looking at processes that occur in both the forward and reverse direction. And again, they're reversible as implied by these two half arrows. And then again, just kind of a reminder of our arrow conventions. So when we see the single arrow, like we've mainly seen in the past, right, we're indicating that most of our reactants are converted to products. And this is kind of implying, right, that they're not going to be going back and forth as well, that it's just going to go from reactants to products. Usually that's some sort of thermodynamic sink. And then again, we have this special arrow to indicate equilibrium, and like we mentioned, right, not to be confused with resonance. So this is actually reactions happening, so we're not just formally moving around electrons. Okay, questions so far? Just don't want to move too fast. Then watching the chat as well. And so then we're just defining our conditions. And so again, much of our interest, and we'll do this in lab, is, okay, we mix our reactants, and then we want to monitor our product concentrations. And luckily, again, the lab is set up that we'll be able to do so by spectrophotometry. So we'll be able to get our concentrations and find our equilibrium conditions. And so we see, again, equilibrium is just defined where the rates of the forward and reverse reactions are equal. So again, right, there's still action happening on the individual molecular level. But as we can see by this graph here, right, our overall concentrations are remaining unchanged at equilibrium. And so, right, highlight this statement again. Okay, so once we're at equilibrium, again, our concentrations are constant. And then obviously, right, this holds true until we perturb it, right? So then, obviously, if we added reactants or products, that would perturb our system. Changing the temperature if it was temperature based, right? Anything, so starting to influence that, then obviously that disturbs our equilibrium. And you can think back to kind of Le Chatelier's principles, right, with that. So you add products, so then that's going to shift it away. Add reactants, again, kind of shift it away towards the products. So that's what we see with our equilibrium. And then, so this is just reminding us, okay, well, we're not saying equal amounts of reactants and products exist. So again, this is something that we would quantify. We're just talking about the reaction rate at equilibrium. And so we'll see, you know, again, where the equilibrium favors. And so we'll kind of look at this, again, quantified with our K value here. All right, so let's look at just, well, how do we express K then? And so our equilibrium constant K, and so this is unitless here. And then notice our formula, right? So we have reactants, products, and then for our equilibrium, it's generally products over reactants, and then it's the concentration, right, taken to the power from our balanced reaction. So just take a second to take in the formula. So yeah, so again, right, our exponent just corresponds with our balanced equation. And again, it's products over reactants. And then the concentration will generally be given in molarity. We will see some cases with partial pressure and ATMs. We'll be able to do similar calculations. But again, for the most part, molarity, and like I said, today's lab will be really good for reinforcing all of that. So just make sure you've copied down, right, our general formula. We'll practice it. And again, always products over reactants. Make sure that, yes, you understand that these are the coefficients from our balanced equation. And so now let's just practice how to write it. Oh, sorry. So just go ahead and take this reaction. So now just rewrite it, right, according to our equilibrium expression. So I'll give you guys a minute or so. So again, I'll just sketch it out. And, maybe you even want to write, okay, products over reactants, just so you don't forget. So then it's my concentration of NO2. Sorry, just trying to. So NO2 to the power of 4 times O2 over N2O5 squared, right? And then we can just scroll down. Again, just double check your expression. So again, that's just our equilibrium constant, right? Expressing our ratio essentially of products over reactants. All right, so now let's try our multiple choice question. So just write our equilibrium constant for our combustion of propane. So there's the balanced reaction. So 1 equivalent of propane plus 5 of oxygen give us 3 of CO2 and 4 of water. So now take a minute or two, which one is the correct one, and then we'll do a little informal poll. All right, so what are we thinking? So any votes for A? What about B? Oh, so everybody likes B. Any votes for C and D? So it looks like everybody is good with this concept. So yes, products over reactants, just checking. And it was balanced. Then CO2 to the 3rd power times the concentration of water to the 4th over propane over oxygen to the 5th. So excellent. And chat agrees. I'm seeing we're all on board there. All right, good. So that's hopefully simple enough. And so then this can start to imply some values. Again, we'll see this again and again when it comes to solubility. So we'll see, right, the value of K and how it makes it more soluble, less soluble. We have, or in this expression, kind of what it's saying, right? So looking at this reaction, we have H2 plus bromine gives us hydrobromic acid. And then they've rewritten our K, right? So HBr squared over our reactants. And then K is a very large number. And again, we can just kind of simplify it, right? Product over reactants. And well, generally speaking, right, and this K is now much, much greater than 1, right? So then that's implying that it is favoring the products, right? So then it's going very far to the right with our equilibrium there. And then, of course, if K is less than 1, and so in this case, we're looking at the equilibrium constant of N2 plus O2 gives us NO, or 2 equivalents of NO. And again, right here's the equilibrium expression, which I think people are understanding, right, how to write this symbolically. So NO2 squared over N2 times O2, and then this is a small number. And so, right, very small K. So again, think about the implications. So products over reactants. So it's favoring the reactants, and that's a good sign, right, for us, because you can imagine what the implications would be if this number was high, right? That would mean that our equilibrium would favor NO if it was the opposite, right? And then what air would we breathe? So that's really good that this equilibrium constant, right, favors nitrogen and oxygen there. So again, just thinking about what that means for our reactants. And then, of course, we didn't really cover it, but we could have, you know, K that's close to 1, and then obviously, right, the implication is that the products and reactants are at least somewhat similar. But obviously, right, you'll have to do math to get the exact value based on the exponent. All right, so let's look at this multiple choice. So what is it implying? So which one is false? So I'll read them and then kind of let you look at them. So when K is much, much greater than 1, the forward reaction is favored and goes to completion. When K is much, much less than 1, the reverse reaction is favored and the forward reaction does not proceed. When K is about 1, neither the forward or reverse reaction is favored, and about the same amount. And then K is much, much greater than 1 implies that the reaction is very fast at producing products. Or are they all true? Excellent. So why do you say D?
Because equilibrium doesn't have anything really to do with reaction rates. All that means is that whenever the reaction reaches its end, it's going to have this approximate ratio or this approximate difference between products and reactants. But it could take 1,000 years for it to get to equilibrium.
Exactly. So that was perfect. I like how you said it right. So equilibrium has nothing to do with rates, right? So like, and that's the thing that we want to emphasize back with our rate law chapter is like we have to have the rate data, right? You have to have the tables. You have to have the time. Like the K means nothing. This only has to do with, right, where the equilibrium is. But like Alex was saying, right, we're not saying what time scale it's reaching this equilibrium, right? So we have to have kind of separate data. So a lot of A lot of data is needed for these. Does that make sense to everybody? We're feeling good? Okay. As long as that distinction is clear, that again, right, we have to have our separate data, we have to have our rate data to determine anything about that. And then we need separate equilibrium data, right, to determine anything about that. Excellent. So you guys are with it. All right, so slowly starting to get into the math of it. And so, okay, so now we're just looking at what our expressions imply. And so we've just written our forward reaction. And so now this is K in our forward direction. So again, just pay attention, right? We have products over reactants. And then of course, right, for the reverse direction, well then now we're just flipping. So now our products become our reactants. So we see that's flipped. And so then the mathematical expression that we'll need later is our K forward reaction is equal to 1 over K for the reverse. So this might be helpful later. Oops, sorry. All right, other relationships that we'll find useful. And so let's say we're given our expression, right? So A plus B gives us C, so there's our K1. Or again, everything's raised to our appropriate power. But then what if we were to double the reaction, right? So now we're saying we're 2 times the amount, so 2 times everything. So then, right, that's like taking everything times 2, so 2 times our coefficient power, or that's equal to K1 times K2 to the n there. So again, just squaring that if we were doubling that. So that'll be useful, again, when we look at how to change and compare rates. And so then what if we have kind of this relationship? And so now we're saying, okay, well, what if we add equations to get a new equation? Then it says the equilibrium constant of the new equation is the product of the equilibrium constant of the old equations. All right, so let's kind of walk through that, just how they got there. So, okay, we have A goes to B here, and then, right, that's kind of our intermediate, and then B goes to C, right? So we can add these equations together such that, right, B will cancel, and then we're just looking at kind of our A to C relationship. And then, so they broke that out, so just doing K1, okay, so that gives us products over reactants, so that's B to the B over A to the A. K2 then, well now, right, B went from product to reactant, so it's on the bottom. And then right from our expression, products over reactants. So then if we just want to go from A to C, well, you can see then how, right, our B's cancel. We can multiply them together. So then our K3 is equal to K1 times K2. So again, from adding those expressions. Now, yeah, and I'll just kind of rewrite it for a second, just kind of showing, right, okay, we added those. So that means the B's canceled, so we were just interested in A to C. But maybe, like numerically, we'll only know the K1 and K2, right? And it'll ask us for K3 as a problem. So I'll just give everyone a moment to write that. Well, it's like kind of additive, basically, is how I would think of it, right? So I don't know, just to, right? Because all you're doing is you're adding these two equations, right? And then notice how B essentially becomes like an intermediate, right? So it cancels. So then if we just want to know our rate from A to C, but will have probably given us K1 and K2, right? So then all we're saying is, well, we can figure out K3 by multiplying the numbers of K1 times K2. If that, I don't know if that helped. Yeah, or without being given like K3. So yeah, I think if you see it, so let's look, we'll start with this simpler one for now. But right, okay, so we're given, and this is again our favorite reaction of the Haber-Bosch process. So then it's saying, okay, at 25 degrees Celsius, we have this K value. But what if we do the reverse reaction and then half our concentrations, right? What is the effect then of our K equilibrium? So take a few minutes. I can always scroll back up if you need inspiration from our kind of rules. So what did y'all do to this original K to find K prime? What do you mean? Like just writing out like the ammonia to the second? Is that what you mean, or? I mean, it's not like wrong, right? I'm not sure that it necessarily like helps us, but we could still just kind of put what that is. But then, right, what we're looking at is, well, what did they do to the reaction? So they flipped it, yeah, so the -1, right? So that's what we're talking about. So, okay, well, we flipped that. And so if we go back to our relationships, okay, well, let's just start with the reverse one. So the K forward is 1 over our K reverse. And maybe we just want to rewrite that first, right? So 2NH3 gives us N2 plus 3H2. Okay, so then from here to here, right, we've just taken 1 over K, or K right to the -1, whatever feels better for you. And then what was the second thing that we did, though? So not only did we reverse it, but what do we do to the concentrations? So then we have them, right? And then if we look back, okay, so once we have them, so then we can take them to that n power, right? So if it's half, we can raise it to the power of a half. So then for that k, that's 1 over k to the square root, right? Or to the 1/2. And so then now we can just solve for k prime. And so I'll punch this into my calculator once I write this. So that's what our expression should look like. And again, just punching it in. So then we should get this for our new k expression. And, you know, again, this is where you could kind of rewrite it as our products over reactants. Again, if it, you know, if it helps you, but I'm not sure that this is as necessary. Yeah. Kind of implication, but this is really, again, what we're going for is how do we manipulate our original equation compared to what we were given there for our k prime. Oh, and then let me write the numerical answer. So 0.00134 we'll round it to. Again, unitless. Questions on this one so far? Yeah, so there'll be a lot of this type of question on the exam and so forth. All right, so let's look at another one. And so see if we can get our equilibrium constant for our first reaction now, given K2 and K3, right? So going back to now the additive concept. So how can we add these two equations, right? K2 and K3, or equation 2 and 3, right? How can we add them? Maybe we have to flip them. Maybe we have to multiply by some amount. And then what would that give us for our new K1? So take some time to solve that. So what do we have to do to equation 2 and 3 to get 1? what are we thinking? Right, compare where your products and reactants are. You got CO2 as a reactant, right? But it's over in the product side. So what do we do? What are you thinking? I see you guys thinking. Don't be afraid to say something. Yeah, so I would do that, right? So let's reverse 2, and then we'll, right, see if that adds up. And then can we, I'm just seeing if we can add up these equations. Okay, so the CO cancels, and then we get CO2 plus 3H2 plus 1 equivalent of water plus 1 equivalent of methanol. So, okay, that works, right? To just reverse 2 and then add them. Okay. And so let's think about all the concepts that we were told. So, okay, we flipped 2. So that means that our new K is 1 over K2, right? And then 3 is still the same, so it's still K3. And then we said, okay, well, if we add 2 equations together, then the K that we're looking for is just the product, right, of that multiplication. So then our K1 is just equal to 1 over K2 times K3, correct? Right, do we all get that? Okay, so then let me just punch it into the calculator so we can verify we're all on the same page here. Oh, well, that's actually pretty easy, right? We can do some mental math. So 7 minus 5 is 2. And so that gives us, right, 140 then for our K value. Questions on that one? And I could also plug it into the calculator, but I always think it's good to practice your mental math skills because anything can go wrong in the calculator. And I would always encourage you to sanity check yourself on the exam, right? At least make sure the order of magnitude looks correct and everything when you're punching it in. All right, that's probably a good spot to take a little break. Did you have a question? I mean, uh, are you saying like you just see it and you just do it type of thing, or I guess. Yeah. Yeah. Yeah, I think it should work. Yeah. Yeah, I mean, I just kind of like looking at it that way, but if like you see it and it all works out, like, yeah, it's not a problem. All right. Any other questions before we kind of take a quick 10-minute break? All right, let's take our break and then we can always ask more questions. made it back from break. All right, looks like the chat is doing well. I think everyone in here is kind of following along. I don't think there's any questions that have come up, but again, just flag me down. And so now we'll look at how we treat our equilibrium constant for gas reactions. And as you can see, right, it's pretty similar. So we have our same just right expression in variables. We see how we put it. Again, right, this would be for molarity. And then we can also put it in terms of Kp. So notice technically, right, this K has a little c if we were to make the comparison. So again, C for our concentration and molarity. Or, right, like this is showing, so our equilibrium constant can be also expressed as our ratio of our partial pressures. And so that is this form. And so that would technically be Kp then. But same sort of general form. And again, right, this is now going to be partial pressure. And I mean, I really don't think we'll do too much of this in class. Like it may come up on occasion. So it's good to be aware because, I mean, we'll see it. And then we should at least be aware of this. Like I said, we probably won't do too many problems with this, but then let's just see mathematically, right, how to go from Kc to Kp. And so just a few reminders, right? Our partial pressures are always in ATM for calculating Kp. And so right away we have an issue because they could have a difference in units. And so we have this relationship where our partial pressure Kp is equal to our equilibrium concentration molarity if we have no change in our moles, right, of our products and reactants. So no change in gaseous moles. And so obviously, right, if we change the number of moles, right, as we go from reactants to products, and we'll see an example, right, like if we go to 2 to 3 or, 4 to 2, well, then we will have a change in gas molecules. And so changing your gas molecules number starts to change your concentration. And so if there is a change, so then we have, well, Kp is equal to Kc times RT to the power of our change in N, right? So that's just going to be our product moles of gas minus reactant moles of gas. And so again, that gives us our change in N there. So let's just practice how a problem may go. And so we're looking at this. Okay, so nitrogen monoxide. And so this is where we want to pay attention to our state of everything. And so we have 2 equivalents of NO, gaseous state, plus 1 equivalent of O2, gas. So then we're saying, okay, well, we have 3 moles of gas in our reactant. But then, right, we only make 2 moles of gas in our product. And so I'll at least give us, right, our change then in N. So just products minus reactants. So then we have 2 minus 3. So we have a -1 change in N, right, for our number of moles there. So I'll let you finish out the rest of the problem. And then we have to get, right, our correct units. And so our R is going to be our 0.0821 for liters ATM mole. And then temperature, right, needs to be in Kelvin. So just like before with these types of gas law problems. So then I'll let you finish calculating the rest. So finding our Kc then. So then looking for answers in the chat, I kind of sketched out the work, just double check that I didn't do something funny. So I just plugged it into our equation and then hopefully did my algebra correct. Do we all get this answer? So some nods. So looks good. So about 5.38 times 10 to the 13th. And so good. I just verifying chat, so sounds good. I just want to make sure we're all on the same page there. Excellent. Questions on this one? Yeah, but remember everything's unitless because it's just like a ratio. Yeah. Yeah, so that's no, because right, it just ends up being unitless. And technically, right, all your concentrations would kind of cancel out to their powers, but yeah, that's why it's just a unitless value. All right, good. So I think you guys have gotten this. So let's look at these practice problems. And so again, right, you're trying to figure out your change in gaseous moles, or if there is a change in or not. And so where would Kp equal Kc? So again, where is there no change in the number of gaseous moles, right, from reactants to products? So take a few minutes, kind of go through these, and then we'll run through them together. So double check those. People in the chat are putting some answers, but make sure you're looking at the states of everything. And so let's start looking at them. So how many gas molecules did we have in our reactants for A? So 2, right? And then how many were in our products? So 1, right? So that's not equal. Okay. So let's look at B. So then how many gas molecules do we have in our reactants? So 3. How many in our products? So also 3. So this one looks good, right? So that is where Kp will equal Kc. And then this one, right, we only have solid, so no gas molecules to 3. So that one will not be equal. So only B has, again, just looking at how many moles are in reactants and products and no change there. Good. Any questions about those? All right, so now let's look at some other kind of equilibrium issues. And so now we're thinking about these scenarios and what it's saying. And so now it's saying, so now we're thinking about heterogeneous equilibrium. And so some of those could be like, what if we're doing some sort of gas And solid phase reaction, I don't know, I'm just drawing stuff. But right, we have maybe a pile of solid that's reacting with our gas. Or what if we're doing, we've mentioned this before, but this term, so when you have a pure liquid, when you have a neat reaction, or again, maybe one of your reagents is a liquid, so then you could do it in that medium. And so what it's saying, and what we want to think about, well, a concentration of pure solid, so again, thinking about this scenario, right, where we have, let's just say it's a gas reacting with a solid, or maybe it's easier for you to think about, like, it doesn't really matter what it is, but some sort of species in solution reacting with a hunk of solid. And so what it's saying is, right, our concentration of pure solid, whether again that be a metal or a pile of carbon, well, that concentration, right, is not going to change. It's just going to be dependent on, right, our surface rate. So dependent upon our concentration of either our gas species or our solution. Or again, right, if we had a liquid neat reagent and it was being done in that, well, again, the concentration is not going to change, right? It's just infinitely concentrated. And so because those concentrations don't change, that means our solids and liquids are not included then in our equilibrium expression. And so this is also kind of a good teaser to how equilibrium will come up again and again in acids and bases. And so this is, right, basically our reaction to form carbonic acid. So we have, right, CO2 reacting with a bunch of water. So just thinking about the ocean even. So obviously, right, a very, very large quantity of water. And so this is not going to change, right, the concentration. So it's not included in our equilibrium expression there. And so instead, right, this is, again, like I said, a small teaser for our acid-base equilibrium. But we can see, so we have CO2, and then makes carbonic acid. And so there's our dissociation. So our acidic proton, so given as H+, and then hydrogen carbonate, right? So our conjugate base there over our initial reactant. So again, in this case, just showing how CO2 forms carbonic acid in that equilibrium expression. So does that make sense? And so again, kind of what you're looking at is, well, this was a liquid. And so again, that's our liquid reagent. So that's infinitely concentrated. And so we see, right, the similar effect for our pile of carbon scenario. And so this is a nice little visual. So it doesn't matter, right, how big this pile of carbon is. We're still just, again, limited by our surface area reactants. And so again, right, our amount of carbon does not affect our equilibrium, but rather the gaseous concentrations do. And so here, right, it's just showing the reaction, but then our equilibrium expression would only have our CO2 over our CO squared. And so looking back, so there's still a question about the liquid. So the thing about the liquid, right, so again, you're like, it's basically infinitely concentrated because this is all your reactant in. But it's different and like kind of confusing maybe because we use a lot of like aqueous solutions in lab, right? But that's different because usually there's some sort of concentration and a molarity. So what we're implying by this water is like that is the reagent, and that's why it's like infinitely concentrated. And this might make more sense if like I said, if we were looking at a different reagent like ethylene glycol or amines tend to be liquid, and again, that would not affect your concentration. But we can think about that and talk about that later if that's still kind of confusing. All right, so see if you can just rewrite or write this, write our equilibrium expression or equilibrium constant expression, excuse me, given this reaction, right? So think about what we said. So solids don't matter. So what's our equilibrium expression? So what's our equilibrium expression for this one? Yep, so CO2. And so, yep, so again, right, we just have a solid, so that doesn't have a concentration. It's just our pile of solid, and then breaks down to make another pile of solid, but again, it's going to be our gas that gives us our equilibrium expression. All right, so just try that again for this reaction. So 4 equivalents of HCl given to us in the gaseous state plus oxygen in our gaseous state gives us water and chlorine gas. And so I'll write out our expression. So again, we're not going to include water since it's our liquid, right? So that's our medium. So then we have, so products to the appropriate power over our reactants to the appropriate power there. And looks like Chet has the correct answer as well. So that looks good for our KC expression there. Questions? All right, feeling good about this. All right, so now we're going to keep getting into the math. And so now it's telling us, and this is what our lab is going to get into, is, okay, the most direct way of finding our equilibrium constant is to measure our amounts of reactants and products. And so again, this starts to depend on like what we can actually detect. And then our equilibrium mixture may have different amounts of reactants and products, but the value of our equilibrium constant will always be the same. And then again, as long as we're at the same temperature. So that's super important, right? So then we're always trying to calculate either our equilibrium or use, right, our equilibrium value to get our reactants and products. And so this is, again, just a good reminder. So the value of our equilibrium constant is independent of the initial amounts of reactants and products. So again, that's what you'll be doing in lab today, is determining your equilibrium constant. And so then we'll get into kind of the math of it. So like I said, this is going to carry on. And I did finally pull up the syllabus after restarting Firefox so we can see right where we're going. So we're just introducing equilibrium this week. Like we're already kind of teasing acids and bases. So acids and bases is a bunch of equilibrium expression. So we'll look at that. And then we'll continue equilibrium, though, into third quarter, which does remind me, register for classes if you haven't already. And then be sure to take the entire series. I know with some majors, especially the engineering majors, they for some reason say you don't need the third quarter of chemistry, but I would just take the year of chemistry so you don't have issues later. Especially, you never know what's going to happen in life, and you don't want to transfer like out of state and someone give you issues later. So just finish the year, take the year of chem. But that being said, we will continue our equilibrium. So obviously buffers and acids and base titration. So that's going to be more acids and bases. And this will be a little bit more intense with equilibrium, but it'll still just be equilibrium. And then like I'd mentioned, we'll get into the actual math of solubility. So then we'll actually quantify those rules that we just kind of looked at. Right, first quarter, we're just like, okay, let's look at these rules. But then we'll get into actually, again, quantifying that. So that will give us a much better look. And so I think that's pretty much the equilibrium. And then you can just kind of peek ahead. We'll go back to thermodynamics and then finish up with other topics. But so equilibrium will carry us, right, for a few weeks. So we're just laying down our foundation. And so that's what we're getting at with here, with this statement. So then, right, we can use our stoichiometry. We can figure out how many reactants or products are being consumed relative to one another. So we'll set up all these data tables, which, like I said, we'll keep kind of walking through. All right, so now this starts to get into more of the math, but it shouldn't be too bad with the math. We'll mainly see quadratic equations, I think, as the most difficult math, so not too bad. All right, so looking at our reaction here. So we have everything in our gaseous state. So CO plus 2 equivalents of H2 give us methanol. And so we have our reaction mixture at 780 degrees Celsius. So this is probably extraneous information, right? We mentioned that our equilibrium constant is the same as long as we're not changing temperature. That's not what we're doing right now. And okay, it initially contains 0.5 molar concentration of CO and a 1 molar concentration of H2. And then it says at equilibrium, our CO concentration is at 0.15 molar. So what's the value of our equilibrium constant? And so now we'll kind of walk through the whole procedure together, but we'll see what it means again with the stoichiometry and how we're going to use that. And so the proper way to solve all these, and again, right, we'll be doing these sort of, I'm going to call them rice tables, ice, right? We can, I just say rice because, like I said, I used to have affiliations with Rice University, so obviously they're going to call it a rice table where R stands for reaction. And so I do like that better. Besides, who doesn't like tasty rice? And so here's our setup for our tables, so outlined over here. So again, we have our reaction, so it's balanced, right? So CO plus 2 equivalents of H2 gives us our methanol, so that's all balanced. And then the ice part, so we have, again, our initial concentrations. And so that's just like what we start with, right? And so this is probably what you'll be doing in lab, right? You'll have your initial concentrations of your reactants. and then you'll let them react, and then we'll measure, right, our final concentration. And so that's, again, what's shown here. So then we'll do the change. And so the change has to deal with, right, these stoichiometries. So that's what it's implying there. And so looking at what happens, right, so this is x and 2x. So then for our change, so this is again, right, one equivalent. So that means it's going to go down by 1x. So minus x, right? And it's being consumed. And so we know it's negative. So right now, again, it's just kind of obvious which direction it's going in because we only have reactants, right? So we have no products, so it has to go in the forward direction. So later on we'll see scenarios, right, where we may have to first determine which direction it's going before we start doing the change. But right now we're consuming all our reactants, they're making products. And then our H2, again, since it's two equivalents, it's going to be minus 2x then, right? And then for our product, so it's just one equivalent, so the change is going to be plus x. So does that make sense so far? Any questions? And so now we can start plugging in some of these values. And again, all these like minor details over what concentration we're actually monitoring, all that depends again on like what's physically capable. So we'll see that in lab, right? So we're going to measure the concentration of a certain species in lab and then figure out, right, our change. And then again, all the math will follow. And so looking at this, what's our value for x here? Right, we can solve that given this initial and this final. So what's x? And so x equals 0.35. And so question in the chat is just asking, is it always negative? And so again, in this case, we do know that it's negative because we started off with 0 products, right? So that's the only way that we knew that it was negative, aka going in the forward direction, right? So there could be other scenarios where we're only given products and then we're going in the other direction, and this would be like minus x, right? It just depends where we are on the equilibrium curve. But we'll do more examples so that you see this. But okay. So just to reemphasize, right, we only had reactants, so we know that it's going in the forward direction, right? We don't know how much. The equilibrium will help us determine that, but we at least know, okay, we're going to assume that it's going in our forward direction. All right, so then we can continue filling in the rest of these values, right? So then plus x, so that means our equilibrium concentration is 0.35 for our methanol. I'm going to solve for H2. Some of you guys can probably do mental math on this, but I'll plug it in. So 1 minus 0.35 times 2, because again, that was minus 2x. So then that gives us an equilibrium concentration of 0.3 for our H2. Okay, so now we're looking pretty good. So now we have our equilibrium concentrations. And so we can plug it into our equilibrium expression now. And so first I'll just write it out in terms of symbols. So we're going to take our methanol concentration over our H2 concentration squared times CO. And now I'm just plugging in the values that we just finished determining. And so now let's solve. And you guys can tell me what you got. I'm just trying to do my order of operations correct and everything. Oops. All right, so double check this value. So did we get 25.93 for our equilibrium constant? I think I saw some nods over there. Everybody get this? Did we get lost anywhere? Good, good. So 25.93. So that's our equilibrium value there. All right, let's try it again. And so now it says, all right, our reaction above is carried out at a different temperature. So right, different temperature, different equilibrium value. And initial concentrations of 0.27 molar of CO2, 0.49 of H2. And this time it tells us at equilibrium, the concentration is 0.11 molar. So how would you find the equilibrium constant? So I'll let you guys try that for a few minutes on your own, and then we'll make sure everybody's on the correct path. And so I'll just start sketching it out while you guys finish that up. And so of course I'm just starting with our reaction from above. All right, so did we all make it to this point at least? So let me know if you didn't, right? Well, let's kind of recap. So I just rewrote our reaction. We were given initial conditions, and again, right, none of our products, so that way we knew we were moving in our forward direction. And then, so we want to map out our change, so minus x, minus 2x, and plus x again. And then, right, they did give us our equilibrium concentration of 0.11 for our methanol. So then we were able to solve for x again, and then get these equilibrium values, right? And so as long as you were able to get the equilibrium values, then you were pretty much home free, right? So then I'll just rewrite our expression just so we're all on the same page. And then plugging in our values that we found at equilibrium. And so let's see what that gives us. So 0.1 divided by, again, just double check my order of operations and everything that I don't do something funny. So do we get this number? Oh, I see what I did. 0.11. Slightly off. So I knew I did something funny. There we go. Does that look a little better? All right. So thanks for checking me on that. So it should be 9.43. And again, showing your work is good in case you are, again, do a little calculator error like myself. So 9.43 for our equilibrium. Questions about these so far? So I don't know how much time we'll have for this next part, but so this starts again kind of explaining, I think, what's troubling a few people. And so, right, we have, basically we'll get into our Q, which I always like calling this our snapshot. And well, let's kind of back up and, well, again, you guys have brought up the concern. Well, how do we know which direction it's going, right? So we have a reaction mixture and it contains reactants and products. It's not at equilibrium. So how can we determine in which direction it will proceed? And so the answer is that sometimes we can then compare our current concentrations, and that's where I say, like, we can take our snapshot, right? If we could just instantly freeze our reaction mixture, okay, what's our concentrations? And then we want to compare that to our equilibrium constant, so we kind of know, right, which way are we going? Do we need to go back and make reactants, or do we keep going forward in the direction of our products? But again, we have to compare that to our equilibrium constant, unless we're in, right, one extreme or the other, like we've seen up here, right? So again, just emphasizing, we started off with all reactants, so we knew it was going to products. We could have had the opposite scenario, right, where you start with all products, so you know it has to go backwards. Otherwise, right, we need to quantify it. And so then this whole Q thing is just our, again, our concentration. So this is basically our K, but not at equilibrium, right? So again, this is where I go, this is just our snapshot. Maybe we'll write not at equilibrium. And so your notes are just trying to emphasize that, yes, right, your Q snapshot is equal to your same K expression. And so that's all that's shown here, right? So that's basically Kc and Kp. So just saying, again, we can look at our snapshot in relationship to molarity, or if we're looking at gases, it doesn't matter. And maybe I'll just re-emphasize that again, right? This is our snapshot, so not at equilibrium with our Q there. But everything else follows, right, the same. All right, so then this answers which way our reaction will go. And so again, we might just want to sketch out products over reactants to kind of keep ourselves sanity checked here. So then we're saying, okay, if our snapshot, if our Q is greater than our K, so right, that's kind of implying we have too many products. Then it says the reaction will proceed faster in the reverse direction. Okay, So just double check that that makes sense for yourself. And so again, we can see that, well, Q is too big, so then we need to go in the reverse direction. And I'll scroll down because I think this little graph kind of helps us as well. So again, right, we're trying to figure out where are we on our equilibrium curve. So right, this is again our K, so our equilibrium value. And then this is just our reaction kind of proceeding around. And so if we're over on this side of the equation, right, again, we're saying that Q is greater than our K. So then, again, it's going to go to the left to form more reactants. And we'll get both the graph and the text, but then, okay, if Q is less than K, so we're saying, again, we need to form more products. So then the reaction will proceed faster in the forward direction. So again, just kind of visually map out where that is. So again, we're saying that Q is less than K, so we're on this side of our equilibrium curve. So yes, it's going to keep proceeding right in the forward direction to the right, making more product. And then what if it just so happens that we're looking at a scenario, and then if Q is equal to K, right, then we can safely say, okay, the reaction is at equilibrium, and again, our overall concentrations are not changing. So we probably won't see this too much, but again, right, it could happen, and again, we're just being conscious of what that means. And eventually, right, our system will reach equilibrium. But again, we're just taking these cues at kind of points prior to the equilibrium and seeing which way are we headed. And then kind of going back to where we started. So, okay, so now we can safely say, again, if our reaction mixture just has reactants, then our Q is essentially 0, and then it's proceeding in the forward direction. And then if it's essentially just products, then Q is going in the reverse direction. But I think it's easier to kind of see these extremes here. So questions so far? And so again, right, we'll have to take our snapshot, figure out where our reaction is potentially, and again, compare that to the equilibrium value. So again, do we need to go forward? Do we need to go backwards? Are we already at equilibrium? All right, so let's look at this. This will probably be our last practice for today. So looking at this reaction, so now we have iodine plus chloride gives us iodochloride, and we're given the Kp of this. So all this is telling us as well is that we're using partial pressures. So we have our Kp of 81.9. We have our reaction mixture, and it gives us these following concentrations. So 0.114 atm of iodine, 0.102 atm of chlorine, and 0.355 atm of iodochloride. And so it wants us to determine, is our reaction mixture at equilibrium, and then what direction will it proceed. So try that for a minute or two, and then we'll go over it together. So I'll just sketch this out. So just start off with writing our K expression just for completion's sake, right? What does that mean? And then good, I'm seeing answers in the chat. And then okay, well this is supposed to equal to 81.9, but then comparing our Q snapshot, so plugging in our appropriate values, so 0.355 squared over my 0.102 times 0.114 there. So what do we get for our Q value? Sorry, what did you say? 0.113? So did we get, so I see thumbs up. And then, so then what does this imply? And chat has the answer, but we'll see. So then which way is this going to run in comparing our values? But it's products over reactants generally, right? And so we still need more products, even though it's getting there, right? So then it'll go in the, which direction? Forward. And then chat said forward as well. And I do see the 10.83 there. So yeah, still going in the forward direction until we again reach our equilibrium value there. Good. All right, so that's a good place to end it. So we'll keep doing these rice ice tables on Thursday, so that'll be good practice to go over together. And again, you can kind of see where we're going. So there may be some quadratic equations involved, but should be fun. All right, any other questions? I'll end the stream soon. And then the labs are there, so I'll see you all in lab for our equilibrium constant lab. So like I said, it'll be a really good lab to solidify this chapter. So I think everybody will feel really good and hopefully have fun.
I don't understand why it's moving forward. Lower than the K value.
Yeah, so then if Q is lower than the K, right, so the K, and again, it's products over reactants. So we're saying that, like, we're not quite there with the products. So we need to keep going in the forward direction to get more, right, to get to that 81.9.
So meaning that as the Q value lowers, it means that there are more reactants that are being produced.
Yeah, but remember, it's just like a snapshot. So the Q is just like literally like we're taking a snapshot and where is it, right?
Yeah.
And so we can only compare the Q to the K. And then we're seeing, right, is Q lower than K? In which case, right, it'll keep going in the forward direction. Or if Q was higher than K, then it would have to go in the reverse, right? Like if it was 100, then we'd say, okay, well, we actually have too many products, so then we got to go back and make reactants.
So is it a total like opposite concept of like the equilibrium? Because we are okay. What I know is that forward reaction is favored when the reactants are produced more than the products.
Yeah, but again, your Q, you're just comparing it to K, right? So they're related. So the K is the equilibrium value, but then the Q is just like your instantaneous snapshot, right? So we're not saying it's done. So then you're trying to figure out, okay, given that we're here, right, and we're not really saying how we're monitoring it, but like, again, that's where the lab is coming into, okay, maybe we're doing spectrophotometry. What if we get it at this point? Which way is it going?
Yeah.
So that's what we're trying to determine, because that'll be relevant, like I said, once we get into it on Thursday more, because, right, we may have to determine, well, which way is it going? Sometimes it's obvious, right? We're starting with all reactants or all products, but otherwise it's not obvious and we got to get a value.
So as the reaction proceeds, Q is theoretically moving closer and closer to
Yeah,
equilibrium.
correct, yeah. So yeah, going back to this chart, right? So it's like depending on where you are. So again, if you're starting here, then it should just proceed, boom, until we're there. It really shouldn't overshoot unless you've done something funny to perturb it, right? Like if you were to add a bunch of products, then that could perturb the system. All right, I'm going to stop this stream. You can email me if there's anything.